Welcome to today's lecture on the second unit of our cellular and mobile communications. So, in the last lecture, we discussed the role of antenna in cellular communication and how the radiation pattern modification is necessary to reduce the effects of co-channel and adjacent channel interference. So, today we will learn the second part of it, of further modification on antenna. So, today's lecture is oriented towards the use of parasitic element. So, what is parasitic element? What is parasites? So, we know that parasites means some living organisms, those are not part of our body, but they live with us, be it temporarily, and whatever we eat as a food, so they get nutrition from that. So they directly don't get that food. What we get or we eat, from that they get their nutrition. So this is the concept of parasites. Then how this concept is applicable for antennas? So what is antennas parasitic elements? That we need to know. Okay. So in the context of antenna, the parasitic element means some metallic structure. Those are not directly connected to the main radiating element, but in shaping the radiation pattern, they have some contribution. So they get the power from the radiating element. Okay. So directly they are not connected to the cable, antenna cable, but they get the radiation from the main element or driven element. This is called in terms of antenna engineering, and they help in modifying the radiation pattern. Now, why modification of radiation pattern is required? So in the last class we described that requirement. So the requirement was, in all direction radiation is not desirable, because if the antenna radiates in all directions, then it enhances the chances of co-channel and adjacent channel interference. So the main goal should be to limit the radiation within that cell. Now, how this driven element and parasitic element work together to create the desired radiation pattern? So that is our goal to analyze. So if you look at this diagram, so this is one layout for Yagi-Uda antenna. So this Yagi-Uda antenna is very popular antenna for television reception, telecom. Okay. So later some advanced version came of this Yagi-Uda antenna, but the main philosophy is similar, that there will be one main radiator that is called driven element. Okay. So that is called driven element. So driven element means this one is the driven element. It's called driven element. Okay. So now these are called parasitic elements. This is also called parasitic elements. So if you look at this, so these three elements that have encircled using a circle, so these are not directly connected to this driven element directly. It is mounted on a boom. That is different. This boom can be metallic, can be made of plastic. If the boom is made up of metal, it means that along the boom, the electric field is zero. So that is why even if you mount this main element or this parasitic elements, actually those are mounted at a point, those are actually having zero electric field. So you can mount by making it metal. So even if these are non-metallic, suppose you have a 3D printed boom and you are mounting this driven element and all parasitic elements onto it, then definitely there is no question of any connection. Okay. So whatever the case is, the main idea is these elements are not directly connected to this driven element. Now what happens? If you can see for this Yagi-Uda antenna, I assume that this main element has a length of lambda. So the antenna length is lambda, means a full wavelength. Okay. So lambda means full wavelength. Okay. Now this is a full wavelength radiator. However, these radiating element, these parasitic elements, these are actually having, for example, this is 0.45 lambda, this is 0.42 lambda, this is 0.4 lambda, and so. Okay. So these type of arrangement, that from this radiating element, whenever it is going like that, so it is dimension is getting reduced or the length is getting reduced. But just the behind this, for this parasitic element, this is longer than this. So the parasitic elements, those are in front of this, these are shorter in length, and this parasitic element which is placed at the back of this, these are actually having a larger length. So then what will happen? So I will come to this change in radiation pattern later. But before that, let us make a short comparison of these driven and parasitic elements. So driven element means electrically connected to the feed line. This is driven element. And parasitic elements means it is in some close vicinity, it is in the close vicinity of this driven element but not directly connected. Okay. So the primary function of this driven element is to create the radiation. That is the primary function, to create the resonance. Because based on this length of the antenna, it will create the resonance. Okay. Now the length is the length of this, I mean the length of each arm is approx 0.5 to 0.55 lambda, and the radiation pattern, suppose these parasitic elements are not existing. So now without this parasitic element, the radiation pattern looks like this. Okay. So without, suppose only this driven element is there, there is no parasitic element. So basically, it will radiate like that. It will radiate like that. Okay. So in one plane, the radiation is like that, and on the other plane, the radiation is omnidirectional because it will have a donut shape of radiation. Okay. donut shape of radiation. It means that if you take the cross section, so it will look like that, but actually the radiation will look like this. So if you take the cross section, it will look like this, but actually the radiation pattern will look like a donut. It means it will radiate in all direction. So in one plane it will radiate like that, like a figure of 8 shape. This is called a figure of 8 shape. And in another plane, it will radiate like in omnidirectional pattern. Okay. So that is why if I use this type of antenna in my cellular system, then what will happen? The radiation pattern not being directional, it will unnecessarily affect the other cell. So for example, if I take this pattern, so it will radiate in this direction and this direction also. And these beam width are very wide. So beam width are very wide. It means what? It radiates in surrounding areas also, not directed towards the main direction line. It is not like that. When you connect some parasitic element to this driven element, then what happens? It focuses the energy towards the parasitic elements. Those are shorter in length. Okay. So the radiation pattern will be like that. It will direct in front like that. And in back, there will be some minor lobes. Okay. So this is the radiation pattern, and the direction where the length of the parasitic elements is actually going shorter, in that direction it will radiate like that. So what was the benefit of this parasitic element then? The benefits are, first is it is converting this figure of 8 shape to a directional shape. Then what is the benefit of this? Benefit is, if the radiation pattern is directional, then the beam will only be focused on the desired cell. It will not unnecessarily illuminate the other cells. This is the philosophy behind developing this antenna, and the name is Yagi-Uda antenna. Now if I come to the next part, why parasitic elements are useful in cellular communication. So parasitic elements, they reduce interference in unwanted directions. Okay. They shape the radiation pattern, because without the parasitic elements, if I cannot change the radiation pattern to some specified direction, so there will be interference. So it helps in shaping the radiation pattern. As it makes the radiation pattern directional, so it improves the signal strength in that desired direction. Okay. Also, it is very important that if the radiation pattern is like that, so this is called main lobe, and in Yagi-Uda, there are some side lobes. I am drawing the radiation pattern completely so that you can understand. So if this lobe is the main lobe, so these lobes are called side lobes. These are the part of the Yagi-Uda antenna. Now, if you can see, this is called main lobe and this is called side lobe. Okay. In between the main lobe and side lobe, there are some regions where the radiation, I mean, the value of the antenna gain is very less. Okay, very less. These regions are actually called nulls. These regions are called nulls. So, by strategically designing one Yagi-Uda antenna, I can create nulls in the interfering regions. Okay. So, if my cell planning is there with me, and if I have all the dimensions, and if I know the positions where the antenna is to be mounted, then by looking at the radiation pattern of this Yagi-Uda antenna, I can place the interfering cells, or I can move the direction of the antenna in such a way that the interfering cells are in the position of nulls. Nulls means very low power. Okay. Or zero. I mean less than zero, negative. Okay. Very negative power. Okay. In dB. This is called nulls. So this type of arrangement actually improve frequency reuse performance, because frequency reuse means I am using same frequency, okay, at some distance. I'm using same frequency. So I should be very careful that when I am using some frequency in this location and I am using the same frequency in this location, these two regions should not interfering with each other by the antenna radiation. Okay. So in simple terms, we can say that these parasitic elements actually responsible for pattern control, which in turn reduces interference. Okay. So this was all about reducing interference by shaping the antenna beam, by creating nulls in the positions of the surrounding cells where the chances are interference are very high. So we can direct the beam toward the desired cell only. Now let us come to the concept of diversity receiver. So what is diversity receiver? So we have learned in the first lecture that whenever a mobile device or mobile station is used in a mobile radio environment, mobile radio means there will be some buildings, there will be some trees. Okay, the mobile station will be moving from one point to another point. Okay, so in that environment, the received signal suffers from fading. So fading means what? Some drop in signal strength. That is called fading. Now short term is there, long term is there. I'm not going into that. Now, when the signal, suppose this is transmitter, this is receiver. So signal can travel. This could be some direct path. This could be some reflected path. This could be some another reflected path. This could be some another reflected path, and so on. Now, if the phase, okay, difference between this direct path and the reflected path are in such a way that they are cancelling each other, so definitely there will be a null or signal will drop. Okay. So that is why it is very important to receive the signal not only through just one antenna. Okay. So if I use just one antenna, then the chances are more that the received signal will be affected by fading. Because at a single point I am standing, and there is a high chance that if due to the position of the reflectors, okay, if the signal is following some pathway, that the resultant phase is just 180-degree between this direct path and reflected path, so we will having some fading effect. So it is always advisable that whenever we will be receiving the signal, we will not use a single antenna. Rather, I will be using multiple antennas. Why? Because if I receive the signal at different positions, then the chances that all the antennas phases are becoming zero. Okay, zero means what? It is reverse 180-degree, not 0, 180-degree. I mean the direct path and reflected path, and so that the amplitude is becoming zero. Okay, so the chances will be very less. For example, at antenna 1, the phases may cancel each other, but at antenna 2, it will not cancel. Okay, so if I don't get any signal at antenna 1, I will get some signal at antenna 2. So the signal strength is not completely faded, or signal strength is not completely zero. This type of receiver where we use multiple antennas to receive signals to avoid fading, this is called diversity receiver. This is called diversity receiver. Now let us come to the space diversity antennas at cell site. Okay. So space diversity means when multiple antennas receive the same signal with different fading envelopes. Okay. When these fading envelopes are combined, the fading is reduced. This effectiveness of the system, because whether the system is effective or not, this depends on the separation between the two receiving antennas. Okay. So suppose two antennas are there. One is this, another is this, and they have some differences. Okay. This is called D, and this H is the antenna height. Then this effectiveness is actually dependent by this ratio H by D. Okay. So from this relationship, this eta H by D is equal to 11 that we should maintain. Okay. So what is the basic diversity receiver concept? So diversity receiver is nothing but two antennas will be there, and then these will be combined by a combiner, power combiner. Okay. So what does a power combiner do? Power combiner looks like this one. Okay. So it can be used as splitter also. So splitter means, suppose if this is the input port, so through these other two ports, there will be half power. It means, suppose I am giving P as input. So here the powers will be P by 2 and P by 2. So this is the concept of splitter, power splitter. Now, combiner means what? Suppose here the power, if suppose P by 2 is coming, and here P by 2 is coming, then the ultimate power will be P. So this is called combiner. So combiner and power divider are basically same things. Just the input and output ports are used in the reverse manner. Now the receiver can combine the signals using different methods based on the scenario requirement. So first is called selection combining. So selection combining means it will only select the branch from where the strongest signal is coming. Equal gain combining. It will add the powers or gains from equally from the two branches. And third one is maximal ratio combining. So it gives priority to the branch where the signal strength is generally more than the other one. Okay. So based on these three combining methods, we can achieve the signal combining. Now, the non-co-channel interference. Non-co-channel means when the interference is not happening between the cells that are using same set of frequencies. So what are those types? So till now we only discussed about one type of co-channel, non-co-channel interference. So that is called adjacent channel interference. So we discussed it many times. Okay. So adjacent channel interference means what? When the interference is happening between two neighboring cells. Okay. So that are using some nearly equal frequency bands, not exactly equals. Okay. Now, two terminologies that we will learn. One is called next channel interference, another is called neighboring channel interference. Now, both are adjacent only. Both are adjacent. But next channel interference means interference from the immediately adjacent channel, just next channel. This is called immediately adjacent. And second is called neighboring channel. Neighboring channel means those are also near, but not immediately adjacent, some nearby frequencies. So these are called neighboring channel interference. Now transmitting and receiving channel interference. So in telecom, one channel, frequency channel is used for uplink, another is for downlink. So this concept already we have discussed. That for GSM 900 example that we have taken, the example of GSM 900. So some channels are dedicated for the uplink frequency, or some channels are dedicated for the downlink frequency. During this uplink and downlink transmission, if there is any interference among these are called transmitting and receiving channel interference. Next, interference from adjacent systems. Systems means these are not the part of those cellular telecom equipments. If some other services apart from the cellular telecom that uses the same frequency band, then also interference can exist. These type of interferences are called interference from adjacent systems. Okay. So suppose police uses some frequency for their walkie-talkie. Okay. If this frequency interferes with telecom services, then this is an example of interference from adjacent systems. Okay. Now, near end and far end interference. So what is near end and far end interference? So two types of users can be imagined. So suppose a user is standing on its own base station, okay, but the signal that it is receiving from the own base station, that is very weak. Okay. At the same time, the user is getting some signal, okay, from the other base stations, but that signal is strong. These type of cases are called as near and far end interference. Okay. So nearby transmitter produces a very strong signal, but my own cell transmitter is producing a very weak signal. So under this case, I am supposed to receive the signal from my own cell transmitter. But as the signal is very low of my own, I mean from my own transmitter, so that is why I am responding to the adjacent channel's transmitter. If the cases are like that, then this is called near and far end interference. Now, a similar type of interference is like near and far end interference between two systems. So, what is the meaning of this? Suppose I am a mobile user. So, I should have uh, get a very strong signal, strong telecom services signal from my own cell. But instead of that, I am receiving a strong signal from some other systems that is not actually telecom, that is something else. Suppose some police Wi-Fi, walkie-talkie signal that I am receiving. If the scenario is like that, so this is called near and far end interference between two systems. So here one system is telecom, another system is police walkie-talkie. Okay. Now crosstalk. So crosstalk means speech from one channel becomes audible in another channel. So earlier it was very prominent. So currently by using several technologies, it has been minimized. So I have called some person, but I am listening the voice of another person. So this is called cross connection. Sometimes in daily life we say that cross connection. So technical terms, this is called crosstalk. Okay. So why this crosstalk happens? So whenever we are communicating through different channels, so there should be some separation or isolation between the designated bands. So if the communication happens in such a way that there is a poor isolation, okay, in the system, so then the crosstalk will occur. So when poor isolation is happening, suppose two cables are carrying signals. One is for channel A, another is for channel B. And there is some interference issue between these two cables, or the cables are not properly shielded. In this case, one portion of the signal from one cable will be coupled to the another cable, and this will lead to crosstalk. Okay. And there are other reasons also, like intermodulation, adjacent channel leakage, interference between systems, and so on. So what is interference between systems? So when two cellular or wireless systems, suppose they're operating in a very close region or vicinity, and one system is interfering with others. Okay, so this is called electromagnetic interference. So suppose one system is the source of electromagnetic interference, and these interference is being coupled to the signal transmission path of the others. So this is known as interference between two systems. Next is UHF TV interference. So it used to happen earlier. Currently, the television transmission is not done in that way. So earlier, some portion of the telecom signal and the ultra high frequency TV signal transmission actually used to share some common region of the operating band. So as a result, what happened that these UHF TV signals used to create some interference effect on the mobile transmission or cellular transmission. Okay. So this is called UHF TV interference. And the final cause of interference is the long distance interference. So what is long distance interference? So suppose two mobile signals are traveling far beyond their intended service area. Okay. So this transmission path could be over water, it could be over land. Okay. So if such interferences become so severe, okay, that it has started interfering with some other cell mobile stations. For such cases, we already discussed in the last class that it may happen if my signal transmission is omnidirectional. So omnidirectional means one antenna will be there. It will radiate power equally in all directions. So the power from that omnidirectional antenna will reach out to a distant place from the designated base station, and it may create interference. So what is the solution for this? That we already discussed, that we need to use some umbrella pattern antenna so that the radiation becomes confined within the desired cell. We will tilt the antenna beam by tilting the antenna at some angle so that the power is not horizontal, power becomes tilted, and so that it cannot escape from the cell. And we should keep a proper antenna height. So if the antenna height is too high, then it will escape the cell. Okay. So these are all about the antenna aspects for reducing interference. Thank you so much for attending this session. In the next class, we will move to Unit 3.